In this project, I was tasked with predicting the electrical energy output, PE, of a combined cycle power plant based on environmental variables such as temperature, ambient pressure, relative humidity, and exhaust vacuum. This is a regression problem where the goal is to predict a continuous target variable, PE, based on the input features. To begin, I identified the key features for the model: temperature, ambient pressure, relative humidity, exhaust vacuum. The target variable is the net hourly electrical energy output, which we aim to predict. These features represent environmental conditions that likely impact the power plant's energy output. For the modeling process, I selected a couple of potential algorithms commonly used in regression tasks. Linear regression, a simple model that will serve as a baseline for performance; random forest regressor, an ensemble learning algorithm that can capture complex nonlinear relationships in the data. This model should perform better than linear regression due to its ability to handle more intricate patterns. After loading and exploring the dataset, I split the data into training and testing sets using an 80-20 split, reserving 80% of the data for training and 20% for testing. I started with the linear regression model. Since it's a simple model, it was important to check how well it performs with this dataset. To evaluate the model's performance, I used 5-fold cross-validation, which helps ensure that the model isn't overfitting to a particular split of the data. Next, I trained and evaluated the random forest regressor model. I again used cross-validation to compare its performance with that of linear regression. The random forest model, typically better at capturing complex relationships, was expected to perform better than linear regression. Once the models were built, I needed to evaluate their performance. For this task, I chose mean squared error and mean absolute error as the evaluation metrics. MSE is a common metric for regression tasks as it penalizes larger errors more heavily, while MAE provides a straightforward interpretation of the average error across all predictions. After training the models on the training set, I evaluated them on the test set using these metrics. Here are the results. The linear regression model has relatively high MSE and MAE, indicating that it wasn't good fit for the data. The base random forest model performed significantly better, with lower error values. Once the performance metrics were obtained, I interpreted the results. The comparison of MSE and MAE between the models clearly demonstrated the improvement achieved by moving from a simple linear regression model to a more sophisticated random forest regressor. In terms of feature importance, the random forest model allowed me to identify which features contributed the most to predicting the energy output. For instance, I observed that temperature and ambient pressure had the highest importance, which makes sense as these environmental factors are likely to have the most direct impact on the plant's efficiency. For a visual summary, I plotted the performance of all models, comparing MSE and MAE across them. This helped illustrate that the random forest model was the most accurate and reliable. In conclusion, after comparing different models and evaluating their performance, I was able to select the best performing model for making future predictions about the power plant's electrical output. In this project, I demonstrated a systematic approach to building a predictive model for the electrical energy output of the combined cycle power plant. I started by selecting the appropriate features and algorithms, then compared multiple models using cross-validation to ensure that the chosen model generalizes well to unseen data. After selecting the best model, I evaluated its performance using MSE and MAE and interpreted the results, providing insights into which features were most important. This process not only helped optimize the model's performance, but also provided a clear understanding of how various environmental variables affect energy output, which could be valuable for improving the power plant operations.